All right, today we're going to dive into the fundamental story of matter itself. We're going to look at some basic concepts of chemistry, but not as a bunch of dry, abstract rules. No, we're going to see it as a human story, a quest to understand the world that's been going on for thousands of years.
I love this quote from Nobel laureate Roald Hoffmann because it just gets to the heart of what we're talking about. He's saying, look, chemistry isn't just about the 100 or so elements on a chart. It's about the creative, almost infinite potential of what we can build with them. It's a science of creation, of transformation.
So let me ask you something. What's the thread that connects, say, the mystical work of ancient alchemists, the life-saving cancer drugs we have today, and, well, the very screen you're looking at right now? You guessed it. It's all chemistry. It's all part of this long, fascinating human mission to understand and, control the stuff that makes up our universe. And our story doesn't start with a complicated formula in a textbook. It starts with people, with history. Long before we had the formal science, people were studying matter because they had practical needs. They had philosophical questions, and they just had this deep, deep curiosity about what the world was actually made of.
And you can really see this evolution in how we thought about it. In ancient India, for instance, Rasayan Shastra was this super practical art. They were perfecting metals, making medicines, creating dyes. Then you fast forward to the age of alchemy, and the goal gets a lot more mystical, right? The search for a philosopher's stone to turn lead into gold. It took until the 18th century for all these threads to finally come together into the structured, evidence-based science we call chemistry today.
And this is where you see this huge shift in purpose. Alchemists, they were chasing wealth, immortality, these grand personal goals. Today's chemists, they're trying to solve humanity's biggest problems, fighting disease with incredible drugs, building the future with amazing new materials. The quest to transform matter is the same, but the goals have become so much more focused on helping all of us.
Okay, so how did we get from those big, sweeping quests to an actual systematic science? Well, it all started with a really basic question. What is all this stuff around us, and how can we even begin to get it organized?
The very first step was just to give it a name: matter. The definition sounds simple, but it's incredibly powerful. If it has mass and it takes up space, it doesn't matter if it's the air you're breathing, the water you drink, or the phone in your hand. It's matter, and that is the subject of all chemistry.
And right away, we can start sorting that matter into three states we all know. In a solid, all the little particles are locked into place, nice and orderly. In a liquid, they're still packed in pretty close, but they can slide and tumble past each other. That's why it flows. And then you have a gas, where the particles are just zipping all over the place, far apart, filling up whatever space they're in. It's all about how those particles are arranged. So once we have the states down, what's the next level of sorting? We can ask, is it just one thing, or is it a jumble of different things? If all its particles are chemically the same, like in a piece of pure gold or a glass of pure water, we call it a pure substance. But if it's a bunch of different things all mixed together, like the different gases that make up air, we call it a mixture. It's the first big way we start to categorize the world.
But wait a second. We keep saying particles, right? What are these things really? To truly understand matter, we've got to go deeper. We have to leave the world we can see and dive into the invisible world of the ultimate building blocks.
And this is where things get really cool. Check out this parallel across thousands of years. Around 600 BCE, an Indian philosopher named Acharya Kendara said that everything was made of these tiny, indivisible particles he called paramanu. Flash forward over 2,000 years, and you have John Dalton in Europe proposing his atomic theory. It's the same core idea. The thought that everything is made of some fundamental, unbreakable unit, it's an idea humanity came up with more than once. It's just incredible.
Dalton's theory really gave us the modern rulebook. He said, okay, everything is made of atoms. Every element has its own special kind of atom, and these atoms combine in simple fixed ratios to make compounds. And here's the kicker. Chemical reactions don't create new atoms or destroy old ones, they just rearrange the partners. That was the blueprint for all of modern chemistry.
But here's the thing. This reshuffling of atoms, it's not a free-for-all. Atoms follow a very strict set of rules. You can think of it like a chemical grammar that tells them how they're allowed to combine. And figuring out these rules was the next huge breakthrough.
So, 3 key laws really laid the groundwork. First, the law of conservation of mass. You can't just make matter appear or disappear. Next, the law of definite proportions. A compound, like water, always has the exact same recipe of elements by mass no matter what. And third, the law of multiple proportions, which is way easier to show you with an example.
So let's take hydrogen and oxygen. They can get together to make water, which we all know. Or they can combine in a different way to make hydrogen peroxide. Now look at this. If we keep the amount of hydrogen the same, the amount of oxygen in hydrogen peroxide is exactly double the amount in water. That simple 1-to-2 ratio was rock-solid proof that atoms were real and that they were combining in these neat whole number units.
Okay, so we've established that atoms are real, and they follow these rules. But there's a huge problem. They are so tiny, and there are so many of them. How in the world are you supposed to actually count them so you can use these rules in a lab? This was the next big challenge.
Just look at that number for a second. That is roughly how many atoms are in just 12 grams of carbon. That's less than half an ounce. It's an absolutely staggering number. Can you imagine trying to do math with numbers like that all day? No way. We needed a better system.
And so to solve this problem, chemists came up with a brilliant idea, a new unit called the mole. The best way to think about it is like a dozen. You know, a dozen just means 12 of something. Well, a mole is just a word for a way bigger number. 6.022 times 10 to the 23rd. This shortcut, known as Avogadro's number, lets chemists bridge the gap between the invisible world of single atoms and the grams of stuff they can actually weigh on a scale. It's like the secret handshake of chemistry.
All right, so let's recap where we are. We have the building blocks, the atoms, we have the rule book, those laws of combination, and we have a way to count them, the mole. So, what can we do with all this? Well, now we can finally start building.
And this is where a big word comes in, stoichiometry. Don't let it scare you. It sounds super technical, but it just comes from the Greek for element and measure. That's all it is. It's the practical math that lets us turn a chemical equation into a recipe we can actually use.
Look at this reaction for burning natural gas. It's like a code, and stoichiometry is the key to decoding it. On the tiniest level, it tells us 1 molecule of methane reacts with 2 molecules of oxygen. Thanks to our friend the mole, it also tells us 1 mole of methane reacts with 2 moles of oxygen. And because we can turn moles into mass, it gives us a real-world recipe. 16 grams of this plus 64 grams of that gives us an exact, predictable result.
And that is the whole point. This is the real power of chemistry. By understanding these fundamental ideas, we go from just being observers of the world to being active creators in it. This knowledge is how we design medicines and how we engineer the incredible materials that are building our future.
So, we've just walked through the basic language of matter, a language that took humanity thousands of years to figure out. It evolved from ancient curiosity into this incredibly powerful tool for solving problems. So the question I want to leave you with is this. Now that we speak this language, what are the next big problems, from our environment to new technologies, that we're going to solve with it? What's the next chapter in this human story we're all going to write?